What we did in the last class was node voltage method and mesh current method, right? Two techniques to the list of tools in simplifying circuits, in analyzing circuits. In this class, we're going to talk about three more techniques, hopefully three more techniques. We'll talk about source transformations, and then we'll talk about Thevenin's equivalent. And we'll talk about Norton's equivalent. So three more techniques into your tool set of circuit analysis. Okay, so what is source transformation? Let's begin with source transformations. The idea of source transformation is a very simple and interesting concept. Okay, the idea is really simple. When you have a voltage source with a series resistance, that can be simplified into a current source with the same resistance in parallel. That's all there is to it. And you can go back and forth. A voltage source with a series resistance can be converted to a current source with a parallel resistance, and vice versa. A current source with a resistance in parallel can be converted to a voltage source with a resistance in series. And they're identical as when we think about the terminal behavior, when we think about the behavior of the circuit with respect to these terminals. This guy is exactly same as this guy. Okay, that's what we mean by the idea of equivalence. Okay, very simple idea is if you want to convert a voltage source into a current source, simply divide the voltage source by the resistance. Then you have the current source equivalent. Similarly, if you want to go back from a current source to a voltage source, all you have to do is, in order to get a voltage source, you have to multiply the current source with its parallel resistance. That's all there is to it. A very simple idea. Okay, and the proof of this lies in the fact that when you compare the circuit on the top, a voltage source with a series resistance, and my claim is that the one on the top and the circuit on the bottom with a current source with a parallel resistance, they're equivalent, meaning from the perspective of this load resistance, the load current flowing through in both of these circuits, okay, that's exactly the same. The amount of current that is flowing through the load resistance in the top circuit is exactly same as the amount of current flowing in the load resistance in the bottom circuit. And why is that the case? Well, that's by definition of equivalence. Okay, when I say the top circuit is equivalent to the bottom circuit, well, the necessary conclusion is that the current flowing through the load resistance is exactly the same. Okay, so when you find the current flowing through the load resistance in the top circuit, you simply get Vs, the voltage applied, by Rs over RL. Okay, and what is the current flowing through the load resistance in the bottom circuit? Okay, that's using the current division. Now, R over R plus RL equate this current and this current because they're equivalent. Then you have necessarily the condition that I mentioned. Okay, so in order to get a current source transformed from a voltage source, simply divide it by the resistance. Okay, so let me say this one more time before we do an example problem. Okay, the idea of source transformation is that a voltage source can be converted to a current source. Okay, how do you transform a voltage source into a current source? Simply take the voltage source and divide it by the series resistance. Then you get a current source with a parallel resistance. Okay, the resistance value does not change. Very simple idea. Let's see if we can do a problem using this guy. Okay, let's look at a problem. Here is an example problem. Okay, the problem is using source transformation, find the power that is dissipated, absorbed, find the power associated with the 6 volts resistance, 6 volts voltage source. The idea is the problem is to find the power associated there. Okay, so what I'm going to do is simply start here, start with the rightmost part of the circuit, apply. So here is the solution. We begin by applying source transform from right to left. Okay, so in other words, specifically what I mean is, let's begin with this. What is that? That's a voltage source with a series resistance. Now what I'm going to do is to leave the rest of the circuit as is. 4 ohm resistance, 36. All of the rest of the circuit is still the same, exactly the same. So here is my 6 volts, 4 ohms, 6 ohms. Okay, and I even leave the 20 ohm resistance as is. I just concentrate on the highlighted pink part, a voltage source with a series resistance. I'm going to apply source transform to convert this into a current source with a parallel resistance. Okay, so in other words, this guy is still 5 volts, 5 ohms. Okay, now I have a new current here, I, whose value is obtained by dividing the voltage source with the resistance. Remember the source transform? Let me go back. The idea is, in order to get a current source, simply divide the voltage source by the resistance. So I transformed a voltage source with a series resistance into a current source with a parallel resistance. Well, how is that useful to me? Well, it is useful because now I can simplify the rest of the circuit. Okay, by observing that there's a 20 ohm resistance in parallel with a 5 ohm resistance. Okay, there's a 20 ohm resistance in parallel to a 5 ohm resistance. What is the equivalent of, what is the equivalent of 20 ohms in parallel with 5 ohms? So that's simply 20 into 5 by 20 plus 5. Okay, it's going to give you 4 ohms. So what happens is this 20 ohm resistance and the 5 ohm resistance in parallel give me an equivalent of 4 ohm resistance, and this guy is still the same. The current source is still 40 volts over 5 amperes, 5 ohms, which is 8 amperes. Okay, so that's my, here I applied source transformation, the first application of source transform. To convert a voltage source into an equivalent current source. Then I applied parallel simplification between 20 ohms and 5 ohms. Now let's see what I can do. Okay, so I'm successively simplifying the circuit from left to right. And one of the approaches, one of the techniques that I'm using is source transformation. Here again, I see a current source with a parallel resistance. So I'm going to apply a source transform again. Okay, I'm going to apply source transform again to convert, okay, into this parallel resistance into an equivalent series resistance. Okay, so that is exactly same, that's not changing, 4 ohms. Now this 8 ohms current source is converted into a voltage source. Okay, source transformation from current to voltage. So what you do is multiply this 8 amperes current by the 4 ohm resistance, which gives you 32 volts. Okay, 32 volts. Now, so this is the second application of source transformation. Everybody with me so far?
Yes.
Perfect. So now the next step is to observe that there is a series combination here. So let me see if I can convert this 6 in series with 4 in series with 10. So that is 20 ohms in series with the 32 volts. I'm going to apply source transformation again. I'm going to apply the source transformation again. Okay, and let's see, let me duplicate this guy. Okay, and by applying source transformation, I'm going to convert this part, the highlighted part, into a current source. Okay, it is the current source with a parallel resistance. Okay, so I have 6 plus 4 plus 10. So this resistance is going to be 20 ohms. Okay, 20 ohms. And then what is going to be the value of this current source here? The value of this current source is going to be 32 volts divided by 20 ohms. So the current here I is going to be 32 over 20, which is going to give me 1.6 amperes. Okay, so all I'm doing is converting a voltage source with a series resistance into a current source with a parallel resistance. And where necessary, I'm going back and forth. That's all there is to it, the idea of source transformation. Okay, if you want to get a current source, divide the voltage by the resistance. If you want to get a voltage source, multiply the current by the resistance. Okay, that's all there is to it. Now let me see if I can further simplify. I can further simplify by noticing that these two resistances, 30 ohm and 20 ohm, are in parallel. So I'm going to leave the rest of the circuit as is, plus minus 6 volts. Okay, there is my 4 ohm resistance, and I can convert this 30 in parallel with 20 and leave the current source as 1.6 amperes as is. I'm not changing a thing. Okay, all I have done is to translate the parallel 30 and 20 ohm resistances into one equivalent resistance. Okay, so 30 in parallel with 20 should give me 30 into 20 by 30 plus 20. Okay, so that's 600 by 50. Okay, which is going to be 12 ohms. So this value is going to be 12 ohms. Okay, now what I can do is I can again, so here is my parallel simplification. Now what I'll do is to apply source transform again. Okay, by noticing that there is a parallel resistance with a current source, I'm going to convert this parallel resistance into a series resistance. Okay, I'm going to leave this guy as 12 ohms and convert this current source. So the idea is the red highlighted current source with a parallel resistance is transformed into a voltage source with a series resistance. So here is my source transform. And this voltage source is going to be 1.6 amperes multiplied by 12 ohms, okay, which will give you 19.2 volts. Okay, so if you, what we can do next is simplify this into a 16 ohm equivalent circuit, but let's find the current now. Okay, now it's easy to find the current. There's one voltage of 19.2 over here. Okay, there's a voltage of 6 volts over here. So what is the current flowing in this direction? I. The current I, okay, and I'm going to call it as I. Current I, all of this is I source. The current I is equal to 19.2, that's the voltage on the right, minus 6 volts, that's the voltage on the extreme left, divided by the total resistance, 12 plus 4, because they're in series. Okay, so you'd get a value of 13.2 by 16 ohms, which should equal 0.825 amperes. So this current is in alignment with the voltage drop here. So the power in 6 volts voltage source is the voltage into current. So that's how much ever it comes out to be. Okay, so that's the voltage drop that's the power absorbed, which is going to be 4.95 watts, and this is positive, it's absorbed. Okay, so the idea is, if I go back and follow what I have done step by step, you will notice that all I have done is to apply source transform a bunch of different times in order to simplify the circuit on the top. I start by applying a source transform. The voltage source with a series resistance on the extreme right is converted to a current source with the same resistance in parallel. Then I applied a parallel simplification between 20 ohms and 5 ohms resistance. Okay, then I look at the blue circuit over here, and now for a second time, okay, for a second time, I apply source transform. Convert this current source on the extreme right with a parallel resistance into a voltage source with the same resistance, 4 ohms in series. Okay, then I apply series combination and apply a source transform the third time. Okay, so all I'm simply doing is convert a voltage source to a current source transform one kind of source into a different kind of source. Okay, and then apply a parallel simplification and then apply a source transform one more time, a fourth time. Okay, then that's all there is to it. I converted a current source to voltage source to current source, and that's all there is to it. That's the idea of source transformation. Does that make sense?
Yes.
Questions, please. Okay, so if you look at what is shown in the PowerPoints here, that's exactly what is shown. Okay, the voltage source with a series resistance is converted to a current source with the same resistance in parallel, so on and so forth. All the steps that I highlighted. Okay, that's all there is to it. And then you can. It's a very simple technique, but very useful technique. In order to get a current source, divide the voltage by the resistance. And in order to get an equivalent voltage source, multiply the current by the resistance. Okay? Source transformation. Now, we're going to add more techniques. So far, we looked at source transformation. Now, we are going to look at a new technique called Thevenin and Norton equivalent. Okay, Thevenin's and Norton equivalent. So this is very useful method. The Thevenin's and Norton equivalent circuit is a very useful method in examining the terminal behavior of a circuit. Okay, so in other words, let's say I have a black box of a circuit. Okay, I have a circuit that looks like this, and I really don't know what's going on inside. Okay, I have no idea of what's going on inside. Okay, now most oftentimes I may not be able to know what's really inside this circuit, and I don't even care. All I care about is, can I represent this mystery circuit as one voltage source with a resistance in series? Okay, if I can convert this mystery box, or if I can express this mystery box into a voltage source with a series resistance, then I don't even have to know what's going on inside the box. As far as these terminals are concerned, A and B, these terminals A and B are concerned, as long as the terminal behavior is same, then I don't have to know what's going on inside the box. I can simply abstract or represent the behavior, the full behavior of the mystery box can be captured by simply using a voltage source and an equivalent resistance. Okay, so this is the idea of Thevenin's equivalent. I'm going to represent an unknown magic box in a simplified version as a simple voltage source with a resistance. And the neat thing is both of these are equivalent. With respect to the terminal behavior, A and B terminals. Okay, so that's the idea. How can you simplify a large circuit into a simple voltage source with a resistance? That's the idea of Thevenin's equivalent. Okay, that's the idea of Thevenin equivalent. If you do the exact same thing in terms of current, that will be a Norton's equivalent. Okay, so if a mystery circuit can be reduced into an independent voltage source and a series resistance, then that circuit is called the Thevenin's equivalent. Okay, the circuit on the right, okay, the circuit on the right is called the Thevenin's equivalent of the circuit on the left. Okay, so if you were to connect a load resistance here, RL, okay, so my argument is if I were to connect a load resistance RL over here and RL, some load resistance, the same load resistance in both of these cases, that experiences the exact same voltage drop and the same current through it. Okay, so that's the idea of equivalent circuit. Okay, so let's see how we can do that. How can we convert, or how can we find? Okay, so the problem will almost always be given in the form of find the Thevenin equivalent of a given circuit. Okay, there are two steps to it. When you want to find Thevenin's equivalent of a circuit, there are two steps. First thing is to find the Thevenin's equivalent voltage. Second thing is to find the Thevenin's equivalent resistance. So in other words, there are two components here. What's the value of Vthevenin and what's the value of Rthevenin? Okay, Vthevenin is defined as the open circuit voltage at the terminals A and B. Okay, and Rthevenin is defined as the equivalent resistance looking in to the terminals A and B. All of this will become absolutely clear when we look at an example problem. Okay, when we look at an example problem. But for now, just bear in mind that there are two steps to finding a Thevenin's equivalent circuit. Find the Vthevenin, find the Rthevenin. So here is an example problem. Okay, the problem is find the Thevenin's equivalent of this guy. Okay, how do you find the Thevenin's equivalent? So in other words, the question really is find one circuit that looks like so, okay, that looks like a voltage source plus minus with a series resistance Okay, the resistance in series. Express all of this circuit, simplify this into one voltage source with one resistance. Okay, so what is the value of VTH? What's the value of RTH? That is, in every respect, identical at the terminals A and B. Okay, if you look at the terminals A and B, the terminal behavior should be exactly the same. Okay, so in other words, finding the Thevenin's equivalent solution here involves finding Thevenin, and another step, finding Thevenin. Okay, there are two steps to it. Let's see if we can follow those steps. Okay, so step one is finding VTH. VTH is defined as the open circuit voltage across A and B. Open circuit voltage across terminals A and B. VAB. Okay, let me see if I can write this V as V. Okay, VAB. How do you find that? Okay, well, let's see if we need to you see the open circuit voltage. Okay, so in other words, let's find the voltage across these terminals here. Okay, so take a minute to look at the circuit on the left and tell me the voltage dropped across the 4 ohm resistance. What is the voltage dropped across the 4 ohm resistance? The voltage dropped across 4 ohm resistance would be R times the current flowing through the 4 ohm resistance, right? But what is the current flowing through the 4 ohm resistance?
Isn't it 0?
It's zero. It's zero because it's an open circuit, right? There is no current flowing between terminals A and B. Thank you for saying that. The current flowing here, I, is really zero. Okay, that's because it's an open circuit. There's no current flowing in here. So all of this is zero, meaning, okay, this V1, there's no voltage drop between V1 and A and B. So VAB, that's the voltage I'm after. That's exactly same as V1. Okay, where that's V1 over there because there's no voltage drop. Okay, there's no voltage drop in the 4 ohm resistance. Now it's easy to find. Let's see if we can apply some of the techniques that we learned so far to identify, okay, to find the value for V1. Okay, so the first thing I'm going to do is to apply KCL. Okay, apply KCL at, let me see if I have enough. I'm going to add a page here. Okay, So copy this guy. Okay, let me copy that guy and clean this up a little bit. Okay, I'm interested in finding the voltage at this node. Let me call this node 1. Okay, so apply KCL at node N1. Okay, if I look at the KCL at node N1, okay, so that's going to be V1. So the voltage here is V1, right? V1 minus 25 volts by 5 ohms. That's the current leaving in this branch. Plus, there is a current leaving down this branch, okay, which is going to be V1 over 20 ohms, okay, plus what's the current leaving this branch, okay, that's negative 3 amperes is the current leaving that branch. All of that should equal 0. Okay, so we have only one unknown variable V1 over here. Okay, and one equation should be enough, which will give you a value of 32 volt. 32 volts. Okay, so V1, which is simply the open circuit voltage VAB, is 32 volts. VAB is the Thevenin, right? So Thevenin is 32 volts. Okay, so V1 is what I was after. Okay, V1. In order to find V1, I simply applied a very simple technique, KCL, at that node N1. So that's step 1. Let me go back. Okay, in order to, what's the step 1 I wanted to do? I wanted to find VAB. Okay, open circuit voltage, okay, VAB, open circuit voltage. And by open circuit voltage, I noticed that VAB is exactly same as V1 because there's no voltage dropped across the 4 ohm resistance. Now, in order to find V1, I applied KCL at the node on top, at this node, okay, to find out a value of VAB or V1 to be 32 volts. So we found VTH to be 32 volts. Okay, now the next step is to find RTH. Okay, the next step is to find RTH. That's step number 2. Let's see if we can do step number 2. Step number 2 is find RTH. Okay, in order to find RTH, what I have to do is to deactivate all independent sources. What do I mean by that? Well, all I simply mean is, if you see a voltage source in the circuit, independent voltage source, replace it with a short. Okay, if you see a current source, replace it with an open circuit. So if you see a source, if it's a voltage source, replace it with a short circuit. Replace a current source with an open circuit. Okay, so let me show that with this example. You copy that. Okay, let me see. Let me add a page here. Okay. So for the circuit given here, I found Vth to be 32 volts simply by applying KCL. Okay. Now, what I want to do is to find RTh. In order to find RTh, I have to deactivate all the independent sources here. What are the independent sources? There are two independent sources. There's that guy and there's this guy. Okay, so there's a voltage source on the left, 25 volts, and there's a current source on the right, 3 amperes. These are the only independent sources. So let's see, in order to find RTh, I'm going to replace this guy, okay, this voltage source with a short. Replace this voltage source with a short and replace the current source, okay, replace the current source with an open circuit. Okay, that's all I mean by deactivating. Okay, by deactivating, all I mean is replace the current source with an open circuit. Now let me try to redraw the circuit here and see what I have. Okay, so there is this 5 ohm resistance and there is a 20 ohm resistance. And of course, there is a 4 ohm resistance over here between A and this guy is replaced with a short. And here is B. Is everybody with me? So there is 5 in parallel with 20, which should give me 4 ohms. So I have the equivalent parallel combination of this guy, 5 ohms and 20 ohms is 4 ohms. So what I have is 4 ohms in series with another 4 ohms between A and B, which is the same as RTh. RTh therefore equals to 8 ohms. So all I have done is to replace the current source with an open circuit. Okay, I open circuited the current. Similarly, I replaced the voltage source with a short. Okay, and then simplified the circuit. And I do this for all independent voltage and current sources. Okay, so that's the idea of Thevenin's equivalent. Therefore, the idea is that Vthevenin is 32 volts and Rthevenin is 8 ohms. Meaning, if you go back to the problem, and this is what you were after, right? Find the Thevenin's equivalent. Okay, you did find the Thevenin's equivalent. In other words, you found the values going back you found the values for Vthevenin to be 32 volts and Rthevenin to be 8 ohms. And that is what we mean by finding the Thevenin's equivalent. Does that make sense?
Yes.
Okay, we look at some more problems in the next class. Okay, these are really simple techniques, but very useful techniques. So in order to find the Thevenin's equivalent, we want to look at the open circuit voltage between these two terminals, open circuit voltage, and the resistance looking in to those terminals. That is called the Thevenin's resistance. And how do you obtain that? You simply deactivate. In order to find the Thevenin's resistance, all you have to do is to deactivate the independent voltage and current sources. Okay, let's see if this is what is shown here. Okay, so finding the independent open circuit voltage and then deactivating, okay, deactivating the voltage and current sources, independent voltage and current sources. Okay, questions please.
Looks good.
Okay, and what I'm going to do is to present to you a sister approach of the Thevenin's equivalent circuit. Okay, let's see. We found the Thevenin's equivalent for a circuit that looks like this. Okay, for a circuit that looks like this, it can be simplified into a circuit that has a resistance in series with a voltage source. This is the Thevenin's equivalent. Now, if I replace this guy with a current source instead, okay, with a resistance in parallel, that simply is called the Norton's equivalent. Okay, that's the idea of a Norton's equivalent. This current is called I Norton. This resistance is still R, the same resistance. Okay, so if I am to express all of this circuit as a current source with a parallel resistance, then it's called a Norton's equivalent. And the same logic at the terminals A and B, the behavior of the circuit is exactly same for the one on the left and the one on the right. Okay, so that's the idea of Norton's equivalent. Okay, let's see if we can do that. Let's see the Norton's equivalent current, which is defined as the short circuit current. Okay, Thevenin's equivalent voltage is defined as the open circuit voltage. Now, Norton's current is defined as the short circuit current. And it's best if I illustrate this using an example problem. Okay, let me see if I can copy this guy. The exact same problem. Okay, and solve it using Norton's equivalent. Let's see, I want to add a page here and say, this is an example problem for find Norton's equivalent. Okay, find Norton's equivalent of the circuit. That's the idea. So meaning I want to find one current source, IN. Okay, so this is a current source. It's a resistance, RTH. Okay, terminals A and B. This is, so this guy is a current, IN. So when you're asked to find when you're asked to find the Norton's equivalent, it simply means what is RTH and what is IN. Okay, finding RTH is exactly the same as before. You deactivate all the independent sources, find the equivalent resistance. Nothing more to it. The exact same thing. Okay, so finding Norton's equivalent circuit has two steps. Just like before, earlier you found VTH, but now you simply find the value of IN. Okay, and step 2 is find the value of RTH. Okay, find the value of RTH. Okay, that's all there is to it. So when we look at step number one, finding I naught. I Norton is defined as short circuit current between the terminals. What do I mean by that? Let me duplicate this, copy, paste. Okay, what I really mean is, in order to find I Norton, pay careful attention. I'm going to short circuit these terminals. Okay, I'm going to short circuit these terminals. Okay, and find the current. So this current that is flowing through the short circuit terminals is defined as I naught. Okay, I'm interested in finding that current. Or in other words, I'm interested in finding the current flowing in the 4 ohm resistance. Does that make sense? When I wanted to find the Thevenin's equivalent, I found the open circuit voltage, right? Thevenin's equivalent is the open circuit voltage, while the Norton's current is the short circuit current. Short circuit current. Okay, let's see if we can simplify this. Okay, so what I'm going to do is to apply source transformation. Add a page. Okay, how am I going to find the current here, I Norton? In order to find the I Norton here, I begin by simplifying from the left-hand side to right-hand side. Okay, so the first thing I'm going to do is to convert this guy, a voltage source with a series resistance, into a current source. So I'm going to apply source transformation. Remember, the idea of source transformation is that a voltage source with a series resistance can be converted to a current source with the same 5 ohm resistance, but that's in parallel now. Okay, so this value of the current source is the voltage source 25 volts by the 5 ohms. So it's going to give you 5 amperes current. Okay, it's going to give you a current of 5 amperes. That is in parallel with the 20 ohm resistance. And then of course, the rest of the circuit is exactly the same. There's a 3 amperes current flowing in there. And then there is a 4 ohm resistance and then a short over here. Okay, and I'm interested in finding this current I naught. Okay, now what I have is a really simple circuit. Okay, what I have is a really simple circuit. Two currents in parallel with two resistances in parallel. So this 5 ohms in parallel with the 20 ohms is going to be 4 ohms. Okay, and then there is this guy. When two current sources are connected in parallel, their equivalent current is the sum of 5 amperes and 3 amperes, which gives you 8 amperes. Okay, so that's this guy. Two current sources in parallel. Similarly, two resistances in parallel give you this guy. Okay, by the same token, okay, let's see if we can identify this guy. This resistance is going to be shown here. Okay, so that's this guy. That's 4 ohms resistance. Okay, now it's easy to find I Norton. Right, remember I Norton is the current flowing through this 4 ohm resistance. What would that be? That is simply the current division, right? So 8 amperes current is branching between a 4 ohm resistance and another 4 ohm resistance. So it's going to be 4 amperes current division, right? So this 8 ampere is going to split equally between the two branches. I Norton is 4 amperes. Does that make sense? So where are my terminals here? These are the terminals A and B. Remember, I'm interested in finding the current IN that is flowing between the terminals A and B. That's A and B. I Norton. I naught is the current flowing between the short circuit current flowing between the terminals A and B. Okay, so if I were to simplify all of the above circuit, so that's all of this circuit. Copy this. So the problem is to find the Norton's equivalent. Okay, so the problem is to find the Norton's equivalent of this circuit. This circuit, I want to express this as a current source with a resistance. Okay, so this is RTH, this is I Norton. Okay, I just found the value of I Norton to be 4 amperes, and I already found the value of R Thevenin to be 8 ohms, and that's the Norton's equivalent. Does that make sense?
Yes.
So Norton's equivalent is simply the short circuit current. If I were to short these two terminals here, what's the amount of current flowing between the terminals A and B. That's called I Norton. Okay, that's what is defined as I Norton. Okay, so let's look back. Let's look back and see if we can find some pattern over here. Okay, so this is the circuit we wanted to simplify. Okay, we wanted to simplify this circuit using Thevenin's equivalent and we also wanted to express this guy as Norton's equivalent. Okay, so Thevenin's equivalent, let me use a different color here. Let me use that color over there. Okay, Thevenin's equivalent came out to be a voltage source with a series resistance. Okay, Norton's equivalent came out to be a current source with a parallel resistance. Okay, a parallel resistance. So the argument was that this terminal A and B, this guy is A and this guy is B. Okay, similarly, this guy is A and this guy is B. Okay, so this Thevenin's equivalent for the circuit came out to be, what value did we get for the Thevenin's voltage over here, VTH?
I think it was 32.
32 volts. And what value of resistance did we see there? 4 ohms, 8 ohms, I don't remember.
I think it was 8.
8 ohms, okay, thank you. 8 ohms. Okay, so the argument was that all of this circuit behaves exactly same as this circuit. So this is the one shown on the bottom left is the exact equivalent of the one shown on the top as far as the terminals A and B are concerned. Okay. Similarly, this guy, all of the circuit on the top behaves exactly same as the circuit on the bottom, where the value of I Norton is 4 amperes, okay, and the R Thevenin is 8 ohms. Okay, so that's the idea of Thevenin's equivalent and Norton's equivalent of the circuit. The same circuit has a Thevenin's equivalent and a Norton's equivalent. Questions, please. Questions so far?
Looks good.
Good. Now, take a look at the two circuits, Thevenin's equivalent and Norton's equivalent, and see if you notice something interesting about them when you look at the two in comparison.
They're source transformations of each other.
Thank you. That's a very astute observation. That's a sharp observation. Thevenin's equivalent is the source transformation of Norton's equivalent. And vice versa. See, I have a voltage source with a series resistance on the left. In order to get an equivalent current source, let's take the voltage source and divide it by the resistance, 32 by 8. Voila, you have that 4 ohms over there. Okay, so the idea is, if you know how to find the Thevenin's equivalent, you can find the Thevenin's equivalent and convert it using source transformation to get the Norton's equivalent. Or vice versa. If you know how to apply or how to find the Norton's equivalent, you simply apply the Norton's equivalent. Okay, you apply the Norton's equivalent and use source transformation to find the Thevenin's equivalent circuit. Okay, so there are two techniques to find Norton's equivalent. You can find the short circuit current directly, or you can find Thevenin's equivalent and then use source transform. Okay, so that's the idea of using Thevenin's or finding Thevenin's or Norton's equivalent. Okay, simple techniques. So what did we do in today's class? Well, we looked at 3 techniques. The first idea is source transformation, which simply means a voltage source with a series resistance can be expressed as an equivalent current source with a parallel resistance. Then we discussed the idea of Thevenin's equivalent, which simply means I can simplify a large complicated circuit into an equivalent voltage with a series resistance. Okay, a simplification of a circuit. Similarly, a Norton's equivalent is a current source and a parallel resistance that represents an equivalent representation of a complicated circuit. Okay? Questions, please. Questions so far. Okay. So that's what is shown here. Find the Norton's equivalent of a circuit. Finding Norton's equivalent means you short the terminals A and B. And then in order to find the R Thevenin, you again apply the exact same thing. You deactivate. How do you find the R Thevenin? Deactivate all independent sources. Meaning, if you have a voltage source, you're going to replace it with a short. If you have a current source, you're going to replace it with an open circuit. Okay, so by doing that, you can eliminate or deactivate all independent voltage and current sources. Then you find the parallel or series equivalent of the resistance looking in to the terminals. So RTH is defined as the resistance looking into those terminals. In order to do that, you get rid of this voltage source from the circuit, the current source, and you short circuit this voltage source, then find simply the equivalent resistance. Okay, when we come back, so the next topic is, let's see. So the next topic is how do you find Thevenin's equivalent when there are dependent current sources? Okay, when there are dependent current sources or dependent voltage sources, how do you find the Thevenin's equivalent? And I don't want to talk about that right now because I don't want to cover too much ground in one day and make it seem like we are rushing. Okay, so in the next class, when we come back, we are going to continue the discussion on Thevenin's equivalent and Norton's equivalent, Thevenin's equivalent, Norton's equivalent, okay, using dependent voltage and current sources. Okay, and there's an interesting technique where you apply a test voltage and test current. Okay, and find the analytical solution for V test over I test to give you a value for R Thevenin. Okay, then we'll talk about maximum power transfer theorem and superposition theorem. Okay, so we are covering more ground and coming to the conclusion of chapter 4, coming to the end of chapter 4. So with 3 more techniques, let's quickly see where we are. Okay, today is the 27th. Okay, we covered Thevenin and Norton equivalent circuits. When we come back, we'll talk about the test voltage and test current method, which simply involves Thevenin's and Norton's equivalent when there are dependent sources, and we'll use superposition and maximum power transfer theorem. So in the next class, we're going to look at more examples. I'll solve some examples for this guy and then move on to talking about that guy. Okay, that will be the end of chapter 4. Then we can start an interesting chapter number 5. Okay, as it turns out, chapter number 4 perhaps is the largest chapter, okay, that we are going to see this semester. And the good news is we are almost towards the end of it. Okay, I'm going to summarize. I'm going to list out all the techniques that you have learned in chapter number 4 and see how we can apply them in chapter 5 and more advanced chapters. Okay, questions, please. Okay, so this is a logical point to take a break. We'll stop here, come back tomorrow, do some problems on what we did so far, and then move on to finishing chapter 4.
Thank you, Professor.
Take care there.
Have a good day.
You too. Bye-bye.